Alright, so we will now look at the hard version of the Omsk metro problem. And I have already explained the problem statement in the previous video for F1. And we will just simply jump into the solution. A disclaimer that I will first try to explain the key idea and the concept, and then I will give you some hints on the implementation part, but it is very tricky and it took me a lot of uh, uh, fails to get it working. So suppose you're given a tree, right? Suppose this is how maybe your tree looks. And let's say this is how your tree looks. And then you in the question, each node, you have two types of queries. The first query adds a node to a tree, adds a node, and the second query will um, ask you that for some u and v, you look at the simple path and you look at all the subsegments in that simple path, and you will have to tell whether the sum is equal to some value k, and each node has a value +1 or -1. Okay, so the first key idea here is that suppose this is your suppose this is your u, and this is your v or any other node, and this is the simple path between them. Then since these values are like +1, -1, -1, +1, whatever, all the segments, right? If you look at all the possible segments and find their sum, then those sums will form a continuous range. For example, uh, basically they will form a continuous range from some L to R, like we discussed in the previous problem. In the previous problem, the paths were from root to some node, but even if that's not the case, it doesn't change the fact that all the subsegments will eventually form the sums will be belonging to some continuous range. For example, if these are the four nodes, then you can see that 0 is a possible subsegment if you don't take anything. +1 is a possible subsegment if you just take this node. -1 is a possible subsegment. -2 is a possible subsegment. And I believe these are the only four subsegment sums, right? And you can see they are of a continuous range. So then I thought that, okay, they are of a continuous range, right? What if I try to find the L and R? I try to find the maximum and the minimum of that range. Because if I can find that, then I can just simply, I then know the range and I can just check if K lies in this range. Okay. So the problem boils down to find for some U and V the maximum and the minimum subsegment sum. All right. Okay. But now how do we do it? So I have divided it into two cases. So the first case is rather simple. What I have done is I have maintained something which I've called as a prefix sum for each node. What does it store? It stores its value is equal to the sum of all nodes from suppose we are we want to find the value of prefix sum for some node v. So from all the nodes from v to root, I will take the sum and I will store that. For example, suppose my tree looks like this. This is +1, this value is -1, this value is +1, and this value is -1. And then there are other nodes in the tree as well, right? Other nodes as well. So the prefix sum for this node will be equal to +1. For this node, the prefix sum will be equal to the sum of all the nodes in this, like from here to the root. So it's -1 and 1 + 1, which is 0. Then for this node, the prefix sum will be the sum of all these nodes, and that would be equal to I think +1. For this, it would be 0, and so on. Okay, so you get the idea, and it's very easy to maintain it, right? Whenever you are adding a new node, you just look at your parent, you know its prefix sum, and you know your value, then you can update your prefix sum. Okay, so this is the first thing that I maintained. Now, suppose a query comes for some u and some v. Okay, and these two nodes, like in the tree, right? In their tree, these two nodes will have some LCA, have some lowest common ancestor. It's very obvious. Let's suppose this was the tree, right? And this is u and this is v. Then the path will go from u to the LCA and then from LCA to v. Correct? So one second, let me make sure I'm recording. Yes. So the path will, like, it will go till some LCA, correct? And the LCA will, let me erase this. The LCA will have its own parent, and then there will be some other nodes as well in the tree, and then suppose the root lies here. But we are only concerned with this path for some query u2v. What did I tell you before? That I want to find the maximum and the minimum score. Okay, so I will show you how to find the maximum, and the minimum will be somewhat the same. It will be exactly the same, just you have to take the minimums, right? So let's solve for the maximum case and try to understand the concept. The implementation, I will tell you how to do it, but it's a little bit difficult. Okay, so the segments, the maximum segment can be of two types. Either it goes something like this, that means it is on both the sides of the LCA. Okay, or the other case is that you have u here, you have v here, and you have the LCA here, you have the nodes. The subsegment having the maximum sum may just either be on this branch or on this branch. So it may look something like this or something like this, right? So, or it may be on both of these branches. So first we will try to assess this case, and then we will try to assess this case. This is a little bit tricky. This is simpler, okay? Suppose that this is a subsegment which has the maximum sum, and this is some uh, node k1, this is some node k2. All right. Now, can you tell me this value? I have given you k1 and k2. Can you tell me this sum using the prefix sums that definition which I told you before? So it will simply be prefix sum. I'll call it PS of k1. So PS of k1 will be what? It will be sum of all values from k1 to the root. Okay, the root will go up ahead somewhere. Plus, I will tell you the formula and then you look at it and tell me if it looks correct to you. Plus PS of k2, what will that look like? That will look like something like this. So you can see that this portion is already covered and this portion is covered. And we have some extra portion as well that we want to remove. So if suppose this is the parent of the LCA, so can you tell me what do we need to subtract? We need to subtract 2 times, because this path, the path from the parent of this LCA, and of course this, the path from the parent of the LCA to the root, right? That needs to be deleted, because that is not uh, that is not going to be lying in this path from k1 to k2 via the LCA. But if you use prefix sums, then it will be included. So minus 2 times prefix sum of the parent of the LCA. Okay, LCA is the lowest common ancestor. And what will be the last thing? So when you do prefix of k1, this path which includes the LCA, the path from k1 to the root goes through the LCA, right? So the LCA will be added once here, and then here the LCA will also be added. So you need to also subtract the value of the LCA, whether it is -1 or 1. Okay, is this formula clear? That assuming that the maximum subsegment path is going from some k1 to k2, then this is how we can represent it in prefix sums. Now, why did I represent it in prefix sums? Because see, for some u and v, which is a query, LCA is fixed. So this is fixed. The parent of LCA is also fixed. This is also fixed. These two values are not fixed. And since we want to maximize this, we will basically try to pick some k1 here such that prefix of, so in the path from the LCA to U, k1 lies somewhere here, right? So we will try to pick the k1 which maximizes, which has the maximum value of prefix sum of k1. And separately from LCA to V, we will also try to find a k2. These two can be treated separately because they are on different branches, and um, we just need to basically find a node which has the maximal prefix sum in this branch and in this branch. Okay. So this is how you solve the first part. Now the question which may come is that how do you even find it? So initially, if you have heard, okay, don't be scared by the name, but if you have heard of a concept known as heavy light decomposition, this is what I thought before. Heavy light decomposition is simply a tool. You can think of it at a tool, as a tool, which is like a segment tree on trees. Okay. And for some node U and some node V, you can do some query on the simple path between U and V. So uh, what we can do is, this is not the final solution. This is just what I thought initially. And you can see here that I got a lot of wrong, like a lot of TLEs here. The HLD solution is correct, but it's not very efficient. Okay. So um, let's put this on hold. Let's put this fact that we have to find it, but let's put it on hold. Okay, we will look at it later. But let's assume that we can find it. All right. So this case is done, assuming that we can find these two values. Now, what about this case? So the first thing that you need to know before moving on is how do you find the LCA of two nodes in very quickly, because LCA will be needed, because we are using the value of LCA here and here. And I will explain this only right now so that next portion will be easier. So if you know how to compute the LCA in log n time, there is a concept known as binary lifting. I would recommend you to read it. Basically, um, suppose there is this node, right, and we want to find its parent, its 10th or its 12th parent, right? Suppose basically its 12th ancestor. So what we create is, and please listen to this because this is used in actually finding this value out. So what we create is we create some sort of DP array, DP of ij, which means that for node I, let's call it node I. For node I, what is its 2 to the power jth parent? Okay. And uh, if we are able to compute something like this, then what we can do is we can divide this path of 12, right, into powers of 2. So 8 plus 4, something like this. So we would try to find dp of I comma 3, which is 2 to the power third parent, and whatever that node is, then from there we have to move 4 places up, which is 2 to the power 2. So we would do dp of this thing and 2. Okay, something like this. Now we will apply the same idea, binary lifting idea, to find these things. Okay. So what I did is I created a DP array. DP of ij meant that if I start at the ith node, and from the ith node, including the ith node, if I look at the basically 2 to the power j nodes above it, which is including it. So basically this node, this node, this node, this node, and these nodes, and these total nodes are 2 to the power j. All right. This is what I represented it as. However, in LCA's and normal definition, it's a little bit different. So the 2 to the power j doesn't contain this node, but I was solving it like this, so I assumed that the ith node is also included in it. So in this section, what is the maximum value of prefix sum? So basically, you have prefix of I here, then you have prefix of parent of I, you have prefix of parent of I, all these 2 to the power j values, all of them have some prefix sums, right? We already calculated that, like from the root to that node. So in this range, what is the basically what is the maximum prefix sum? And if we somehow, if we are able to create an array like this, so if I want to find out this value, like um, from U to the LCA, what is the node which has the maximum prefix value? So suppose there are total 20 nodes between U and LCA, including both of them. So I could break that into powers of 2, which would be 16 nodes, and then 4 nodes here. And then what I could do is I could first do dp of U, and I want to look at these 16 nodes. So it should be 4, 2 to the power 4. And then um, whatever this node is, we can compute it by LCA concept only. Then suppose this is node um, P. Okay. So we'll do max of this and dp of P comma 2 to the power 2. So 4 nodes here. So something like this. So that's how in like log and time also, it's just similar to like how binary lifting works. You divide the range into powers of 2, and then you greedily like choose those powers of 2, and you have already pre-computed the answers for those ranges. So I know this is why it's implementationally a little bit tricky, and you have to, like, there are not the sample cases are not very um, like they are not very good. They usually they passed most of the times, and then I got a wrong answer. So you have to be very careful about this calculation, okay? And make sure that you are including all the ranges and including things correctly. But we are more or less focusing on the concept here, okay? So this is how you can identify this value and this value. Basically, just from U to LCA, you know how many nodes are there, and you divide that into powers of 2. And then for all those segments, you can try to, you have already made a DP array which stores the maximum prefix sum. So this is how you will solve this portion in order log n time. Now, coming on to this portion. This is also again very simple, but it uses the same concept of this uh, power thing. Okay, so you have this LCA and you have this U, and we are assuming that the answer lies somewhere here. I will create another DP array. Let's call it DP2. So okay, I will first explain what I am trying to do. All right. Basically, I want to find um, I want to find the maximum, right? So if I divide this exactly in half, this range, if I divide it exactly in half, it might not be divisible exactly in half, but let's assume that we are doing it. And let's say that for this range, we know that if we only consider subsegments in this region, suppose this subsegment and this subsegment, only know we know these subsegments, and we know what is the maximum of all of these. Suppose let's call this M1. All right. So we know the maximum sum of the subsegments here. Similarly, suppose for this region, we also know the same thing. We know that if we look at all the subsegments in this region, from LCA to this half position, right? Let's call this M2. So our answer will be This is not the complete answer, but it will be maximum of m1, comma m2, comma. What part is not? So from U to LCA, right? What type of ranges are not covered now? All the ranges which are starting somewhere here and ending here, like which are starting to this part of the middle and ending to that part of the middle, they are not being considered, right? So we need to now consider all of these ranges. So if I know, so suppose this is some node, uh, let's assume that out of all of these ranges which are starting here and ending there, like to the right of the half, suppose this is x1 and this is x2, and I'm saying x1 to x2 has the maximum sum. Okay, just bear with me for a second. X1 to x2 has the maximum sum. So what can I write this as? I can write it as prefix of x1 minus prefix of x2 is the maximum. X2 my x2 parent of x2 actually, but because x2 like prefix of this minus prefix of this, so these two will be minus. So this should be maximized. So how can I maximize this? Well, basically, if in this region I try to identify the x1 with, so you can see, right, this x1 lies in this region, this x2 lies in this region. So in this region from U to the mid, if I can find the point which has the maximum prefix sum, okay, so I find the point having the maximum prefix sum, and in this region I find the point with the minimum prefix sum. So it's very obvious that their difference will be the maximum, because this is the maximum out of maximum prefix sum out of all the uh, nodes in this region, and in this region this node has the minimum prefix sum. So since we the sum if on a range is something like this, I am maximizing this and I am minimizing this. So this क्या कहते हैं, this sum will be maximized. Okay, so this will be the third thing, maximum 1 minus maximum 2, minimum 2, minimum 2. Okay, let's say. And how do you find it? We have already discussed somewhat before, right? In this range, you want to find the maximum. In this range, you want to find the minimum. So you can do this concept of binary lifting, which I told you. You know, you can, using that DPRA that you had originally made, you can sort of find the maximum in this range in the end. So that's how you do it. Um, you basically construct two DP arrays. The first DP array, it's like a binary lifting DP array. So the DP1 of ij tells you that from I up till including I, if you go up to 2 to the power j elements, what is the maximum prefix sum in that range? Similarly, you also need the minimum prefix sums, right? So there will be total into 2, there will be total 4 arrays, but we are considering only the maximum case right now. Okay. So in this region, what's the maximum prefix sum? And the second will be, and this is used, this prefix array is used in the first case where the paths are lying from in this type of region. And for these types of paths, um, you need to know um, the second DP array. So DP2 of ij tells you that from I and you go 2 to the power j elements, including I, out of all the segments in that range, um, what's the maximum segment sum? Okay, and using using that information, you are able to find the answer. Okay, now I told you here in this case that we are assuming that there we are partitioning it into half, but that might not always be possible. So if you have heard of sparse tables, right, how they function, so we will do something similar to find the partition. What we will do is we will simply suppose this is U and this is LCA, and suppose there are let's say Suppose there are total 6 elements, okay? 1, 2, 3, 4, 5, 6. So I want to partition it into basically, see, this array, right? The second array, it stores from I to 2 to the power j. So I need to separate it into two sections of 2 to the power j, uh, because then I can directly do like dp of starting point and then this whatever power is there of 2. So in this case, what we will do is we will try to find the maximum power of 2, um, which is such that we just cross the mid. So in this case, if we look at number 4, which is 2 to the power 2, and we include 4 elements, and similarly, if you include 4 elements from here, so we will simply do something like dp of 1 and 2 to the power 2. So from 1, and look at these 4 elements, out of all these subsegments, what's the maximum? And from 3 basically we need to know the starting point. So dp of 3 and then 2 to the power 2, basically 4 elements. What we want, we are fine with overlaps because that won't change our answer, but we don't want to take a power of 2 which is less, like we don't want to take 2 to the power 1. Okay, why? Because if we take 2 to the power 1, then um, if you have like 1, 2, 3, 4, 5, 6, then only we'll be able to divide it into two ranges. Okay, and this middle portion will be empty. So want to pick a like a larger power of 2. And if you know sparse tables, then you probably know how you find it. It's I think it's log of um, mid log of r minus l plus 1. I think this is it. Uh, s- so that's how you find the power of 2. And then um, since you are given these two ranges, and now what you want to do is, okay, so in these two ranges, this is the region of overlap. You want to now find all the extra segments will be the segments which start to the left of the overlap and end to the right of the overlap. So some segments like this, these segments are not included. So you need to you need to find the maximum prefix sum here and the minimum prefix sum there, um, and then you take their differences. I will explain some more implementation details, like how do you update um, the DP tables. So let's look at that as well. So DP table update is very simple, just like binary lifting. So if you want DP of ij, that would be maximum of, I think, DP of um, I minus 1 j. Like you divide, basically it's 2 to the power j, so you divide that into 2 to the power j minus 1 and 2 to the power j minus 1, comma dp of I minus 1. It's 2 to the power I in this case, uh, and j is the index, and whatever is this position, so this is j, this is 2 to the power j elements, and then this is suppose k. So uh, something like this. That's how you update the dp table for the prefix max, and similarly you do the uh, so this is dp1 for the prefix max, and dp2 ij is a little bit more complicated. So suppose from here you want you are considering 2 to the power j elements, and you want to find, okay, for all the segments, um, what's the maximum segment score. So what you do is you divide into half, like 2 to the power j minus 1 and 2 to the power j minus 1. This will be easily computed. You already know, like this would be dp2 of uh, I minus, I'm mixing things up, so this should be I minus 1. It doesn't matter if I hope you are able to understand. Like one of these means the node and the other one means the power. So I am assuming the first one to be the power. So 2 to the half power, and then j is the starting point, and this is again half power, and whatever this k is. Okay, you can find this k if you know binary lifting and all that. That's why I said it's implementationally a very tricky problem. And then you also need to look at the segments which start here and end here. So you do the same thing. You find the basically the maximum prefix sum here and the minimum prefix sum here, and you subtract that. That will be your third thing, and you take the maximum of all of them. Okay, so yeah, that's some implementational details. The crux of the problem is this, that you can divide it into two parts, and then um, these are two types of parts, and then both of them have to be treated separately. All right, I will show you the implementation if you want me to, but it is very horrible. Okay, so okay, like I said that this is like the DP for the prefix. This is the DP for the all from I to 2 to the power j of all the subsegments, and we have to make DP for maximum and minimum as well. And then this is how you update the DP, and basically from j all the way till 2 to the power I minus 1, and then the new like the for the other segment, whatever the starting position is, which is I have made it as L2, and L2 is the um, like from j you go 2 to the power I minus 1 steps ahead, and then you take its parent. Okay, and okay, this is very complicated. There's not like not complicated, but it's a lot of verbose. So uh, now suppose a query. Okay, so what am I doing here? Okay, yeah, this is this. So this code here just updated the prefix DP array, which was easy. But for the normal the other DP2, you need to have the third case as well, which I told at the end. So uh, this like you take the minimum, you take the maximum to the left and the minimum to the right, and then you subtract that. And the maximum and minimum, uh, I just queried that from the sparse max prefix which I made. And then for each query, if you're not following with this, it's fine. But for each query, I'm finding the LCA. Then I'm checking if like a path of type 1 can exist or not. If it can exist, then I uh, I divide the path into two parts. I find the so this basically gives me the prefix max and the prefix min in a range from L to R, from V to LC in this case. And then I take their maximum values and then subtract that, which I told in the very early stages. And then you also subtract the prefix of the parent of the LCA. And then once this type of case is done, then I've made another function to solve the second type of paths. So this basically takes a range, and in that range, from like the range will be like U to LCA and the V to LCA. So both of the ranges you want to find the subsegments. And then it's again a lot of work is being done here. Um, so first you need to find the split, then you need to find all the points of the split. For example, I told you here there are basically 4 points which are important: the start, the exact end, and then these regions. Uh, the point just right to the overlap, and the point just left to the overlap. Okay, basically these points and these points. So these 4 points are important, and using these 4 points, I this query function just tells you the prefix max in a range and the prefix min in a range, and then using that I am just I'm like taking my answer as the maximum to the left and the minimum to the right. So yeah, it's a lot of code, but it seemed to work quite well. Initially, like a lot of complexity can be reduced if you because I'm using sparse tables here, right? That's why things are very complicated. But if you use HLDs, then the code becomes a little bit simpler. But the issue is that the time complexity is like I could not get an HLD solution to pass in the time constraints. All right. So yeah, that's it. Thank you for watching. Uh, I will see you in the next video. Bye bye.